So up to this point, we've been using the derivative of the position to get the velocity and the derivative of the velocity to get the acceleration, but you can actually go the other direction. You could start with acceleration and integrate to find the velocity, and then you can start with the velocity and integrate to find the position. The difference is you have to be given some initial conditions, the velocity and the position at t equals 0 or some time. So these two problems, 51 and 53, are where we have to integrate instead of take the derivative. So typically we start with acceleration and then we calculate velocity and position. So 51 says, a rocket starts from rest and moves upward from the surface of the Earth. For the first 10 seconds of its motion, the vertical acceleration is given by a sub y is equal to 2.8 meters per second cubed times t, so that's linear. What is the height of the rocket above the surface of the Earth at t equals 10 seconds? What is the speed of the rocket when it reaches 325 meters above the surface of the Earth? So what we're going to do is we're going to start with, all we're doing is talking about when this rocket is accelerating with this particular relationship. So the relationship is that the y component of acceleration is equal to 2.8 meters per second cubed times t. Again, t is seconds. Seconds times meters per second cubed gives meters per second squared. Now, we have to start with some initial conditions. Well, initially, the velocity in the y direction at t equals 0 equals 0 meters per second. It starts from rest. Also, the y value at t equals 0 is also equal to 0 meters. So those are my initial conditions. So what we know is that the velocity in the y direction as a function of time is the integral from 0 to t of a sub y of t dt. So instead of taking the derivative, we take the integral. Now, one thing to do is to use a variable other than, what we'll do is we use t star here as our upper limit, because here we're using t. So t star is a particular time. T here is just the variable. So now what we're going to do is we're going to stick in the expression for a sub y. So you get 2.80 meters per second cubed times t, that's a sub y of t, times dt. Well, this is a constant, so you can bring that outside the integral sign. So then we just end up with the integral from 0, t equals 0, t equals t star of t dt. Well, the integral of t dt is just going to be t squared over 2. So we get 2.8 meters per second cubed times t squared over 2 evaluated between 0 and t star. And actually, yeah. So what we're doing here is, to be honest, you got to take this integral gives you the difference between the velocity at some time t star and the velocity at 0. So you can do this as an indefinite integral, or you can do it as a definite integral. I'm using the definite integral, so I'm going to show this difference in the velocity is equal to the integral of this thing. Okay. Now if you plug in t star and 0 in the appropriate arrangements here, so you get v of y at t star minus v sub y at 0. Okay, 2.8 divided by 2 is 1.4. So you get 1.4 meters per second cubed. And what you get is you get t star squared divided by, don't need to divide by 2 because I just did that. So let's just get t star squared minus 0 squared. And if I solve for the velocity as a function of y, I get that t star is equal to vy of 0 plus 1.4 meters per second cubed times t star squared. So the original acceleration was linear. The velocity is a quadratic. Now vy of 0 is 0, so we can just say that v y of t star is equal to 1.40 meters per second cubed times t star. So that's one way of doing it. The other way of doing it would be to say that the differential of the velocity with respect to, actually the derivative, so this is the way this works, dv sub x of t dt, so that the derivative velocity is the acceleration. And this should be this should be y is equal to the acceleration as a function of time. Okay, so you multiply both sides by dt. And then what we do is we integrate. So you integrate both sides. So this is solving like a differential equation, which we'll get into the second semester of calculus. So the integral of the derivative is just the velocity as a function of time. And here we integrate a sub y, which is 2.80 meters per second cubed times t times dt. Now, here we don't have limits on the integral. You'll see what happens in just a second. So when you integrate this, you get the same thing. You get 1.4 meters per second cubed. That comes from the dividing by t squared over 2. So I'm going to divide that. So I get t squared. And you add this arbitrary constant c at the end. And then you use your initial condition. And your initial condition is that v sub y of 0 equals 0 meters per second. And that's to evaluate c, the arbitrary constant. So v sub y of t at t equals 0 is 0. So if I put 0 in here and I put 0 because it's 0t and 0 because it's 0 meters per second, so I get 0 meters per second is equal to 1.40 meters per second cubed times 0 seconds squared plus c, and you get see that c equals 0 meters per second. So that's my arbitrary constant. So what I can say is the velocity is the y velocity as a function of time is just equal to 1.40 meters per second cubed times t squared plus 0. So I'll put it in there, but you know, we can, even though it has units, we can just drop it. And we get the same answer. Notice this one is a function of t and not this t star. Okay, so let's do the same thing to find the displacement. Remember the derivative of y of t with respect to t is the y component of the velocity. So if I multiply both sides by dt, I get dy of t is equal to v sub y of t times dt. And then I integrate both sides. Again, I'm using an indefinite integral without limits. So that's basically what we had over here with velocity, right here, dv sub y dt equals async. So we have the same thing here, except using the derivative of the displacement with respect to time as velocity. So when you integrate that, you get y of t equals the integral of v sub y of t, but that is equal to 1.40 meters per second cubed times t squared. So that's v sub y of t is that, and you multiply by dt. Okay, so the integral of t squared dt is t cubed over 3. So what I get my constant, which is in front, and then I multiply by t cubed over 3 using the rule for integrating polynomials, plus this arbitrary constant c, which is different than my arbitrary constant c in the previous problem. So my initial, now I need to figure out what this arbitrary constant c is, so I use the initial condition again. In this case, I use the displacement that says y at t equals 0 meters. So y of 0 is the value of t. This 0 is the displacement. So I get 0 meters equals 1.40 meters per, let me put divide by 3 there, 1.4 over 3 meters per second cubed times t, which is 0 seconds cubed, plus c, and you see I get 0 seconds cubed times 1.4 over 3 meters per second cubed. Here I'll get 0 meters, here I have 0 meters, so c equals 0 meters. So that's my arbitrary constant, 0 again. So I get that the y displacement as a function of time is 1.40 over 3 meters per second cubed times t cubed plus 0 meters. And you can just drop this into 0 meters. Okay, so I have what I need now to solve the problem. So it says, what is the height of the rocket above the surface at 10 seconds? Well, all I have to do is plug in the number in. So y of 10 seconds is going to be 1.40 divided by 3 meters per second cubed times 10 seconds quantity cubed. And let's see what I get. 1.4 divided by 3 times 10 cubed is 467 meters. Okay, that's the answer. Okay, then it says, what is the speed of the rocket when it is 325 meters above the surface of the Earth? So in that case, we don't actually give you t. So what you're going to do is you're going to take the displacement of 325, put it there, solve for t, then use that t in the equation for velocity, which speed is the same thing. Velocity, so it's just not a vector. So what we're going to do is part B is 325 meters equals 1.40 divided by 3 meters per second cubed times t cubed. So if we divide both sides by this, we'll get t cubed is equal to, Well, what you'll notice is that what we have is 325 meters. And then we take the reciprocal, 3 over 1.4, and we take the reciprocal of the units, seconds cubed over meters. And you see the meters cancel out. We just end up with seconds cubed. So you get 325 times 3 divided by 1.4. So we get 696.4 seconds cubed. And take the cube root, or to the 1/3 power. And you get 8.86 seconds. Okay, so that is the time when the displacement is 325 meters. Now notice here at 10 seconds it was 467. At 10 seconds is 886. That makes sense because for lower time it's less displacement. Okay, so now that you have that time, all we have to do to find the speed is we go back and use this expression right here, which says v sub y of t is equal to 1.4 t squared. So we know that v sub y of t is equal to 1.4 meters per second cubed times t squared. Make sure I did that right. 4 meters per second cubed times t squared. Okay, yep. So v sub y of 8.86 seconds is equal to 1.40 meters per second cubed times 8.86 seconds quantity squared. And this, you notice the units will become meters per second because you have seconds squared divided by seconds cubed, which would be 1 over seconds. Okay, 1.4 times 8.86 squared, 110. So the velocity at 325 meters, which corresponds to 8.86 seconds, is 110 meters per second, which is the correct answer.